Hello everyone, welcome to today's session. My name is Wycliffe Akumba, and in today's session I want to share with you how you can obtain digital elevation model data or elevation data or altitude data for your region of interest for analysis. And in today's session, first of all, I will show you the regions of interest where we want to do the mapping. For example, first of all, I need to set the background of the mapping environment or mapping area to satellite so that we can clearly see the locations of our interest. So we can get the elevation data for this region. If we want to set up an experiment in this tea growing region, somebody might want to know what is the height above sea level of that location. What about this other region? What about this other region? What's about other region? I mean, elevation is important because tea only grows preferably above 1200 or 1500 meters above sea level. So the knowledge of how high a location is important. And this can also help us to get the slope of a location, which we are going to see how to do in a very simple mapping process. Okay, so in our Google or in our Google Colab or Google Colab, we can simply import our two libraries, that is Earth Engine and GMap, right? And then after importing them, we need to authenticate our credentials. So we use Earth Engine to authenticate, and then we can initialize the project. These are the two ritual kind of codes that we have to deal with. Okay, so for our initialization, we need the project ID. So we go to our name here and then project info. We grab this, copy it, and then you go to your Colab and paste it, right? Once you pasted it, you run that, and it will ask you to allow Google Earth Engine. Then you select your name, then you continue, and again you continue, and then you will have your Google Colab connected to your Earth Engine environment or Google Earth Engine credentials. Okay, then let us, for example, identify the names of locations where we want to do our study. So we can call them sites or places or something. And then maybe sites is a better. Okay, let me just call them places for now. Okay, so you want to do your study or set up your experiment in Kericho. You want to set up your experiment in a region called Nandi. You want to set up your experiment in a region called Kisii, and you want to set up your experiment in a region called Kirinyaga, as well as in a region called Meru, right? Places. So these are just places within Kenya, and I'm sure tea is grown in all of them. But these could be in Tiolo in Malawi. Somebody could be doing them in around Mata Tea Factory in Rwanda, or somebody could be doing them in Cameroon, where we have tea, or DRC, or Uganda, or Mozambique, or South Africa, or Zimbabwe. All those countries we have tea, or Ethiopia up here to the north. Cool. So we start by visualizing the map using GMap, and we pick the map function. Then we provide a base map of satellite so that we can see clearly the tea farms, and then demarcate our tea growing regions of interest, right? So I will start with Kericho. I will follow the list. So starting with Kericho tea growing region, I want to pick a region that borders both large and small scale tea farming. So I will take this dragging and drag it around there. That's enough for me. Then I go to also Nandi. I also pick a region which borders both small scale and large scale tea farmers. I'm not biased in that sense. I don't want to be biased. And then in Nandi, maybe this is Sotik, but around Sotik and Nandi and Kisii region, I also pick a region. They are not necessarily exactly equal area, but I'm just getting the general idea about the elevation. So again, in Kirinyaga, we pick a region that borders both large scale and small scale tea farmers. And then we go to the far north, probably the northernmost tea fields in Kenya. And then we pick borders, both large scale and small scale tea farmers. Okay, so we have picked all our 5 tea growing regions in a very simple manner. Kericho, Nandi, Kisii, Kirinyaga, and Meru, right? So once we have those points, we need to convert them to what Earth Engine understands. So I can call them sites now, and then I say from the map, draw features, just like that. And then if we run sites, we'll see, sorry, the spelling here is not right, like that. We can see the 5 features drawn or provided as a list. And once we have them as a list, the next thing we need to do is to convert this list to, or to add names, to add the names of places which we defined here, to append them to each of these, because currently they are just features without names. So to give them names, we can say for the sites, for each feature, set a name, right? That is what we want. And we want to call it from name for F and name in a combination of both sites and places, because we called them places. Again, if we check sites, it's still a feature, but then we can now convert this our site into a feature collection, right? So we use EE feature collection, and we apply this EE feature collection on the sites so that we can see the feature collection sites. Each of these feature collection now has an attribute called name or a property called name, and it picks the name of each site. So we start with Kericho, then we have Nandi, then we have Kisii, then we have Kirinyaga, and then lastly we have Meru, right? So those are our 5 features in the collection. Then after getting the features in the collection, we can go ahead and create a elevation map, or we obtain elevation data, and the elevation data we will get from SRTM. SRTM at 30 meters. There is SRTM, this one here, which is at 90 meters, I think. Yes, it's at 90 meters, but the one we want is the second one, which is at 30 meters. You just type in SRTM and it shows you the SRTM, which is at 30 meters. Again, important to read the description here so that you understand the image you are working with. So we copy the collection snippet and we take it to our coding environment. Okay, so we provide it there. And then if we check, if we run elev, it will be an image. It's an image with a band called elevation. And that band called elevation contains the height above sea level of each site, throughout the world. Now, if we want to get the elevation of any of our features or each of our features, so I can call them stats or statistics, we can say from the map of the whole world, from the elevation data for the whole world, I want you to do a reduction over regions, right? Because I have regions, I have 5 regions. So do for me a reduction across those regions. And the regions are in an object, called feature collection. So the collection, we call it FC, as we defined up here. Then the reducer, which I want you to use, this is the operator which you want to use to bring all the pixel values in each region together. We are going to use EE reducer dot mean for this, for instance. So we want to get the mean altitude within each region, right? So we add bounding box or some polygon. So within each of these polygons, something like this, within each of these, we want the mean elevation, because inside here alone, there are several elevation values because the resolution is 30 meters for our data. So there is 30, 30, 30, 30, 30 meter resolution, and each of those 30 meter resolution has their own height above sea level. The height above sea level in this stream is different from the height above sea level in this airstrip. So we want to get the mean for this region because we want to set up an experiment here, and we just need a general idea of elevation in that region. Scale, we will set to 30, and then we can see what the stats return. All right. So for the stats, we get a feature collection, and the feature collection has got the 5 features, but now we have 2 properties. The first property is the mean, which is the height above sea level of this feature, and then the name is Kericho, right? This may be different from what you already know about the height above sea level or elevation of Kericho, but it is because of the location we picked. So if you were to check for the elevation at this particular place, just near Kericho town to the south, or southwest of Kericho town, then you will realize that average elevation here is around 1933. The same to other places. You might have some elevation data which is different from that, but should be close to that if you are within the same region, right? So those are the stats. But those stats, they are in a feature collection, which for some of us who don't want to know much about Earth Engine, don't need. So we can use GMAP to convert that feature collection to a data frame. And when I talk of a data frame, I mean something like a CSV file or Excel file or just column and rows, something like this. So we have mean elevation and we have the names of the sites. So the function which helps us to do that is gmap Earth Engine feature collection, that is, to data frame, right? Very simple. Okay, so once we have this data, this is the elevation data, you can export it to your content here and download it. So you can just say df dot to CSV, and then you give the CSV name, maybe elevation or sites underscore elevation. It doesn't matter the name you give here generally. And when you run that and refresh here, you see your site's elevation. You click the 3 dots and you download it, and you have your elevation of the 5 sites, right? From this elevation, you can see that Kisii was the highest. The region we picked in Kisii had the highest altitude, followed by, I think, Kirinyaga, then Nandi, then Kericho, then Meru was the lowest altitude of the 5. It all depends on the selection, on where you picked, because it can vary. So it's experimental site specific, right? Your experimental site. For example, if I were to drag another region here, it will be a different elevation from what we have down there. Okay. So you can export that to CSV, and all is simple. I said we can also do slope. So for slope, you can use the 11 you can use the elevation and then you convert it to a slope. So to do that, we use the Earth Engine terrain dot slope, and then we provide a lev as the image. And then if we print slope, we will see our slope here, right? And then for this slope, we can do the extraction just the same way we did with elevation. We can get the slope for each region. We can call them start slope. We'll get slope and then reduce region with the feature collection, reduce a mean, scale 30, the same. And then again, we get the slope. So it's also a feature collection with 3 columns. And each feature has 2 properties. Yeah. So we have the slope, which is the degrees, slope in degrees, about 5 degrees in Kericho, about 4.7 in Nandi, um, 9, almost 10 in Kisii, quite steep slope there, and Kirinyaga around 5.7, and then in Meru, quite steep, very, very steep. The location we picked, not overall for Meru. Please, you cannot cite this information as the overall slope in Meru unless you used the whole of Meru bounding box. Okay, or polygon. So DF for slope, we can get it from gmap dot Earth Engine to where? To a data frame. And then what do we provide here? The stats slope feature collection. And then if we check DF slope, then we see those values that we were struggling to see. Okay, something is not right. Start slope, gmap, EE to DF, and then slope. Okay, this one is not right. So it should be DF slope. Okay, so we can see that Meru is the steepest of all the slopes. The maximum should be 90 degrees. Like the steepest slope you can think of is a 90-degree, like vertical wall. And of course, on a vertical wall, you cannot grow a T. Okay, so very fast, if you want to visualize this, then if you want to visualize this, of course, to export it is the same way we exported data frame. You just write it to CSV, and then you get it here and you download it. What I want to show is, for example, if you want to visualize it, I mean, no need at all. You can just import matplotlib dot pyplot as PLT, and then you use the PLT dot figure, and then you say what is the fig size. You want, for example, a fig size of 10 by 5 as a tuple, and then you provide the plot itself. I like bar-h for this, and then you provide the DF, for example, DF slope, which is the data frame for the slope. And then from DF slope, we pick maybe name to go on the x-axis. And then DF slope, we pick mean to go on the y-axis. And then we color it as maybe steel blue. You can pick any color of your choice. Okay, and then after that, we can also provide PLT. Sorry, not plot, but PLT dot GCA. This is to help us arrange the bars in descending order. And then we say invert y-axis, and then that will ensure that the plots show us which is the highest, which is the second highest, up to the lowest slope. And then we can put the labels, PLT label, X label, sorry. And then on the x-axis, we can say elevation, not really, yeah, because now we've inverted the axis, so we can say x label is slope in degrees. You can pick the degree symbol, and then we can say plt.title is slopes. For now, we just say across sites for the sake of time. And then we can say plt.tight layout to make it fit nicely in our plotting area. And then we show it plt.show. Okay. There is a problem. There is double. Where did I have that? Color still blue. There is a problem. PLT bar H df, we pick the name. Okay, here. I think we need to close this and then df slope, and then we don't need this one here. Okay. Okay, we need to sort these values. Yeah, we need to sort them. So we can say df slope is equal to df underscore slope dot sort by our sort values themselves. And then we use the mean values so that they are sorted, and ascending we set to false so that we don't, we sort them in descending order. Okay, so that should work. Yeah, now you can see, let me reduce the zooming. You can see the sides. Meru had the steepest slope of around 13. Kisii follows, and then Kirinyaga, Kericho, and Nandi at the least slope. I mean, not so much necessary, but it's something you can visualize in any other software of your choice. You can take your data into R, you can take it into Excel, you can take it into whatever plotting or visualization tool you want or you prefer. All right, so with that, we are able to extract elevation data for our regions. We don't need to fuel any vehicle to travel to all these places to get the height above sea level of any of these sites where we want to establish our experiments or anything else. Again, this has nothing to do with tea. Also, you can do it for any other location globally. It doesn't have to be tea. It can be coffee, tobacco, or miraa. Again, you can do it for other countries. You can go to South Africa, you can go to Malawi, you can go to Tanzania, Burundi, Rwanda, Uganda, Congo, Madagascar, you can be in Sri Lanka, Indonesia, Australia. It doesn't matter. Globally, you can extract the elevation data. It doesn't have that it doesn't mean you must be working on tea or on a crop. The value of elevation data, you might need it in very, very many different places. For example, in this case, we might be interested in encouraging people in Meru to grow their tea away from steep slopes or ensure or enforce more conservation, soil management practices in the tea fields in Meru than in Nandi. So they have to account for this, because if there is erosion, if there is mass wasting, and those kinds of denudation or soil loss, then Meru might be affected worse than Nandi. I think at some point we had a story of somebody's tea field going into a neighbor's compound. Like there was that landslide where soil and farm and plants from one person's compound were dragged down to another person's compound. So who owns those tea fields now, or those tea plants? Can you just start plucking tea and taking to factory because it's in your land? But it was brought by nature. Finally, this work has been done meticulously by the following group of people. So it's important always to look at the citations part as well as the description, terms of use, and then you can comfortably report your work. So it's important to recognize these people, like to cite them, right? They are the people behind this, not Google Earth Engine. Google Earth Engine is just a platform that enabled you to easily interact with the data, get the data, analyze it, and present it. Thank you for listening.